Dear students, today let us discuss on a new topic, herbicide selectivity and adjuvant and their use in herbicides. A large number of factors such as plant, herbicide and environment operate simultaneously for a herbicide to become active and selective to a plant. Herbicide, while moving through a plant system, may be blocked, detoxified at several possible points, and as a result, differential activity and selectivity are achieved. To offer selectivity to crop plants, the herbicide should be less mobile, if not completely immobile. Adjuvants are chemically and biologically active compounds, and they may improve the effectiveness of the herbicide they are added to, either increasing its desired impact and or decreasing the total amount of formulation needed to achieve the desired impact. Some adjuvants enhance the penetration of herbicide into plants by ensuring adequate spray coverage and keeping the herbicide in contact with plant tissues, or by increasing rates of foliar and or stomata penetration. Let's now discuss the selectivity of herbicide. Selectivity of herbicide refers to the phenomenon by which in a mixed stand of plants, some plant species, especially weeds, are preferentially controlled or killed, while crop plants remain unaffected or negligibly affected when a herbicide is applied to them. It is an important factor towards weed control through herbicides and crop safety. It is resulted from the differential response of plant species to herbicides, and it is a complex phenomenon achieved by complex interaction between plant, herbicide and environment. Selectivity refers to its potency towards control of weeds without affecting crop plants in a mixed stand. Selectivity of herbicide is largely dependent on the time, method, rate and formulation of herbicide application, environmental conditions, plant species and stage of growth of crop and weeds. In order to know the selectivity of herbicide, we are using a new term, selectivity index. Selectivity index SI is the ratio of maximum dose of herbicide tolerated by the crop to the minimum dose of herbicide required to control weeds. The higher the selectivity index, the greater is the safety to the crop, and vice versa. If SI is greater than 2, the herbicide is safer to use without much fear of crop damage. If SI is less than 2, the proper method of herbicide application is to be adopted, and care must be taken to apply the herbicide strictly at the recommended rate. Selectivity index SI is calculated as maximum dose of herbicide tolerated by a crop divided by minimum dose of herbicide required to control weeds. Next, we will discuss on different kinds of selectivity. At least one kind of selectivity must operate when herbicide is applied to crop, although usually more than one kind of selectivity operates under a given situation. There are 4 major types of selectivity. They are: number A, physical selectivity; number B, chemical selectivity; number C, biological or biochemical selectivity. It is also known as true selectivity. And number D, chronological selectivity. Number A, physical selectivity. Physical selectivity to herbicide is achieved by manipulation of physical factors or environment. It could be achieved due to manipulation of the following factors. The factor number 1, depth protection selectivity. Selectivity of herbicide achieved due to protection in depth of sowing of crops is called depth protection selectivity. Number 2, externally working antidote mediated selectivity. Charcoal or activated carbon is a good example of externally working antidote mediated selectivity. They absorb certain amount of herbicide applied to soil and interfere directly with uptake and indirectly with the metabolism of herbicide, thereby decreasing herbicide uptake as well as risks of damage to crops. Number 3, application device protection selectivity. Non-selective herbicides are made selective to some standing crops by modifying the application technique or device. Number 4, selectivity to non-selective herbicides. Non-selective herbicides could be made selective by modifying the crop environment. Number B, chemical selectivity. Selectivity achieved due to structural changes, changes in functional groups and or side chains of the phenyl or benzene ring of the herbicide is called chemical selectivity. Number C, biological or biochemical selectivity. It is also known as true selectivity. Selectivity due to metabolism of herbicide or reverse metabolism of herbicide inside plants is called biological or biochemical selectivity. It is inborn and can hardly be manipulated by extraneous factors, at least at the recommended dose of herbicide. It operates invariably for every herbicide. Differences in morphology and physiology among plants make groups of plants affected or killed by herbicides, while others unaffected in a mixed stand of plants. Number D, chronological selectivity. Selectivity achieved due to manipulation of the time of application of herbicide is called chronological selectivity. It results from the application of same herbicides as pre-planting, pre-emergence or post-emergence. For example, pendimethalin is selective to most crops when applied as pre-emergence but not as post-emergence. Similarly, early post-emergence application of some herbicide at 15 to 20 DAS, means days after sowing, may result in greater selectivity than their late post-emergence application at 30 to 35 DAS in many crops. Let us now discuss factors affecting selectivity. Factors affecting selectivity of herbicide are: number A, plant factors, number B, herbicide factors, number C, environmental factors. Let's start with number A, plant factors. The plant factors include anatomy, morphology, and physiology of plants, varying plant architecture, growth behavior, biochemical process across plants are highly responsible for imparting herbicide selectivity to plants. The plant factors include: number 1, morphology of plants. Number 2. Physiology of plants. Morphology of plants is discussed as: Number A. Location of growing points of plants. The growing points of plants are located above ground, at the surface, or below ground. They affect the interception and retention of herbicides and play a great role if the herbicide is systemic. Number B. Leaf or foliage or canopy. Broadleaf plants have bigger leaf size, greater area, and horizontal orientation of leaves that are likely to intercept more amounts of herbicides than grasses that have erect, narrow, and upright leaves, thus reducing selectivity of herbicides. Plant or leaf surface having pubescence, waxy surface, roughness, and corrugated leaf reduce amount of herbicide contact and absorbed by them, thus reducing effect of herbicide. The rooting depth of a plant is also a basis for selectivity. Herbicides like triazines remain mainly in the upper layers of the soil and affect the plants whose roots lying in that zone of soil. Number 2. Physiology of plants. Plants' tolerance or susceptibility to herbicide is largely dependent on the herbicides themselves and the genetic makeup of plants. For example, 2,4-D, 2,4-dichlorophenolic acid kill broadleaf leaves or weeds, while most narrow-leaf monocotyledonous plants or crops remain tolerant. Plants differ in sensitivity to herbicides because of their differences in morphology or physiology, such as: Number A. Uptake or absorption and translocation. Differences in morphological features such as leaves, stems, roots characteristic, and the age of plants result in differential uptake of herbicides by plants, which results in differential translocation of herbicides inside plants. Number B. Metabolism of herbicide. Metabolism is the most dominant mechanism in support of herbicides selectivity to plants. Plants differ in their ability to metabolize herbicides. Once a herbicide has entered into the plants, metabolism is faster than accumulation in some plants. As a result, there hardly any residue of herbicide builds up at the site of action inside the plants, and plants show tolerance, whereas reverse is true for the plants showing susceptibility. Number B. Herbicide factors. Herbicides within a class differ from each other as well as have some common physical and chemical properties which render them selective or non-selective to a group of plants. Moreover, herbicides within a group show different degree of activity and selectivity, mainly due to their difference in molecular structures. Selectivity of herbicide also vary depending upon the type of herbicide formulations. For example, soluble concentrate SC, emulsifiable concentrate EC, wettable powder WP are applied in spray form, which cannot differentiate plants by virtue of their desirability, crops, or weeds. Therefore, the chance of achieving selectivity is less. But in granular formulation, herbicides are broadcast or placed depending on the requirement. Hence, degree of selectivity is obtained under both pre-emergence and post-emergence applications. Time, doses, method, or device of herbicide application and adjuvants also affect selectivity of herbicides. Number C. Environmental factors. Environmental factors play a dual role. They affect physiological and biochemical processes for plant growth and development in one hand, and absorption, translocation, and metabolism of herbicides on the other. Plant species respond differently to environmental factors such as temperature, sunlight, relative humidity, rainfall or moisture, soil texture, etc., and therefore have differences in growth and development, which may lead to differential absorption and translocation of herbicides across plants. Under severe stress conditions, plants may not function properly. Metabolism of herbicide may be insignificant, and as a result, a normally tolerant plant may fall susceptible to a herbicide. Let us now discuss adjuvants. Adjuvants are a group of substances or chemicals with varied nature and chemistry and are added to improve surface wetting, increase penetration, facilitate slow release, improve translocation, and reduce drip and evaporation, and to extend persistence of the herbicides. Adjuvants are also called additives because it facilitates and accentuates the emulsifying, dispersing, spreading, and wetting properties on other surfaces, and thus modify the properties of liquid and improve the herbicidal effect. Adjuvants do not increase the innate activity of herbicides but help its availability at the action sites of plants and thereby indirectly increase their efficacy. Adjuvants used in herbicide. Adjuvants are classified in three different categories, such as number A. Activator adjuvants. Activator, it is also known as synergists. Number B. Spray modifier adjuvants. Number C. Utility modifier adjuvants. Number A. Activator adjuvants. Activator adjuvants increase herbicidal activity. It has been grouped into number 1. Surfactants. Number 2. Phytoblend oil and oil surfactants. Number 3. Other activator adjuvants. Number 1. Surfactants. It means surface active agents. A surfactant is a material that exhibits activity at the surface or the interfaces. All surfactants lower the surface energy of solvent both in oil sprays as well as in aqueous sprays. They increase spray retention at key sites, increase penetration by increasing area of contact with the leaf surface, act as humectants and solubilizing agents, facilitate movement along cell walls after entry by lowering interfacial tensions, provide safety to the operators, and increase overall biological properties of herbicides. Number 2. Phytoblend oil and oil surfactants. Phytoblend oils are used in preparing oil-water emulsions for post-emergence spray of atrazine in maize and sorghum and other herbicides. Phytoblend oil surfactant concentrates contain 80 to 83% phytoblend oil and 17 to 20% surfactant. Number 3. Other activator adjuvants. Isoparaffinic oils, ammonium thiocyanate, urea are commonly used activator adjuvants. Urea enhances the 2,4-D phytotoxicity and reduces its rate of application. Number B. Spray modifier adjuvants. Spreaders, spreader stickers, and foaming agents or drip control agents are the spray modifier adjuvants. Spreaders and spreader stickers are mainly used in insecticide and fungicide. Stickers hold the toxicant in intimate contact with plant surface and reduce wash-off from the leaf surface. Foaming agents or drip control agents are materials used in liquid spray mixers to reduce spray drip. So, herbicide liquids are sprayed in large droplets to tackle this problem. Example, invert emulsion. Besides these chemicals are used to increase droplet size. Number C. Utility modifier adjuvants. Utility modifier adjuvant includes number 1. Stabilizing agents, number 2. Anti-foam agents, number 3. Compatibility agents, number 4. Buffering agents, number 5. Oils, number 6. Humectants, number 1. Stabilizing agents. Stabilizing agents are of two types, number A. Emulsifiers, number B. Dispersants. Number A. Emulsifiers. Emulsifiers cause emulsion concentrate to disperse spontaneously into small and stable droplets when added to water. They substitute for constant physical agitation of the spray liquid during field operation. Number B. Dispersants. Dispersants stabilize suspension. They keep fine particles of wettable powders under suspension in water even after initial vigorous agitation has been withdrawn from the spray tank. They act by increasing the hydration of fine particles of wettable powder laden within the herbicides. Number 2. Anti-foam agents. Anti-foam agents are usually silicone that is often dispersed in aerosol cans or plastic squeeze bottle, especially in areas with soap water. Farmers often use kerosene or diesel fuel at 0.1% for eliminating foam in spray tank. Number 3. Compatibility agents. Compatibility agents are used for dispersing emulsifiable herbicides in liquid fertilizers. For example, 2,4-D, Alachlor and other herbicides are applied along with liquid nitrogen fertilizer. Number 4. Buffering agents. Buffering agents increase the solubility of herbicides in water. Number 5. Oils. Oils are added to increase the activity of herbicide and in some cases can act as herbicide themselves. Number 6. Humectants. Humectants prevent rapid drying of herbicide sprays on the foliage, thus providing an extended opportunity period for herbicide absorption. They are hygroscopic in nature. Herbicide selectivity is very important in crop production. Through selectivity, it is possible to use a herbicide specific to a particular weeds without affecting the main crops. The efficiency of herbicide also enhanced by adding adjuvants which reduce the cost and doses of herbicide application. Thank you.